Signals and systems is one of the most fundamental subjects in engineering and applied sciences. Why is this discipline so important? One of the main reasons is that we all rely on information, and signals is the carriers of that information. So we can define signals as the carriers of information or this information itself. Generally, we can say is this as a set of information. Once signal is received, we can extract the information it contains. We can then process this information, modify it, combine it with new information, and finally transmit the result. To perform these operations, we need a device. Generally, such device contains of interacting components and called system. So, system is a device that transforms a set of input signals into another set of output signals. Now, let's concentrate only on signals. Our next question is, how can we measure a signal? There are different types of signals. For example, this signal varies over time, and our question is, how can we measure such type of signal with one number, with one single number? If we choose as a measure the area of a signal, if we write energy of x equal to integral from minus infinity to plus infinity of x of t dt, it will be incorrect measure because plus and minus signs will cancel each other. If we choose absolute value, it will work. But physical meaningful measure is to choose the square of this signal. Power of a signal is the limit when period goes to infinity, 1 over t, from minus t over 2 plus t over 2 x of t squared dt. Power is the rate of delivering energy per time. So now we explain why we've chosen the square of a signal as a measure of our signal size. From physics, we know that instantaneous electrical power is the product of voltage to current. Or we can rewrite it as current squared to the resistance of the load, or the voltage squared over R. So here we can see that power is proportional to the square value of the current or square value of the voltage. Next example. Intensity of sound wave, or power per unit area. It's a square value of the pressure of sound wave over the density of medium to the speed of sound. Here again we can see that intensity or power per unit area is proportional to the square value of the pressure of sound wave. Third example is power density of electromagnetic wave or Poynting vector. It's a product of electric or magnetic field intensities. Or we can rewrite it as electric field intensity squared over intrinsic impedance of free space, or as like this. So here again we can see that power density is proportional to the square value of electric field intensity or magnetic field intensity. So our choice for as the measure of signal size, the area under the square value of signal has physical, meaningful basis. But here we can see that everywhere we multiplied or divided by the constant of resistance or another variables. And here we divided signal by 1. Energy of signal depends not only on signal but also on load. And we have properly normalized. And then our measure will be correct.